Thank you all for your patience and welcome to our exploration of our econ application. And specifically, we're going to be talking about the calculus of profit maximization. So when we're talking about the calculus of profit maximization, the first thing that we need to break down, especially since some of us may not be familiar with economics or business, right? What is this notion of profit, right? And when we're talking about profit, we're really just talking about the money that comes in, or our revenues, and then we are subtracting our total costs. And with these things, it's often best to use an example, right? So if we have a lemonade stand, and if I tell you that the lemonade, each one is sold for 50 cents. And if I tell you that, you sit outside for 8 hours, and that's going to result in 500 cups that are sold. Let's say it's Fair Trade Days or something like that, right? It's a popular time. So this right here is our quantity. This is our price. And so when we're calculating these individual parts here, right, our revenue is equal to the price times the quantity. And so this is going to be equal to that 50 cents times 500. So half of 500, which is 250. And this is going to be denominated in dollars. So this is my revenue. So just making sure we're all on the same page, just in terms of what things are called. Now, when we're talking about the flip side, right, our cost, once you get into microeconomics, you'll find there are multiple different ways of costs. There's costs that stay fixed. There's costs that are variable. When we're talking about costs, right now we're just going to keep it to just variable costs, but we'll complicate it in a little bit here. And we're going to say that the costs is going to be, so each cup costs, and we'll say something like maybe 5 cents per cup. We'll say each cup of lemonade mix is going to be equal to something that is increasing in the number of cups. So we'll have something that is, 0.2, and then the number of cups, right, which we'll use as x for here, to the second power. So instead of having it just be 0.2 times x, we're going to have it be 0.2 times the amount that we're making. Let's say that, we have to squeeze more and more lemons as the day goes on, and it becomes more arduous, and our hands start to cramp, and we get less and less and less since we're making homemade lemonade mix with sugar and lemons that we are hand squeezing. And so putting our costs together, we have something that looks like costs is equal to 5 cents times that cup plus 0.2 cents times the amount of cups squared. And if we go back here, right, we can rewrite this in that same kind of terminology and say that our revenue is equal to 0.5 times the number of cups that we are selling that day. So now we can also plug in this 500 number into our X here to figure out how to calculate what our profit is when we sell 500 cups, right? So on your own, go ahead and do that.
Is that 0.2 in dollars or cents?
Thank you. That should be in cents. Yes. So this actually, so let's take a big step back here. So this one is 0.05 cents, and this one, since I did say 0.2 cents and then I miswrote it, well, so this one is 5 cents, this is 0.2 cents. But then when we're talking about costs in terms of dollars, right, then what I have to do here is this is actually 0.002, which makes a heck of a lot more sense. I was like, why are we operating at a loss? Lemonade stands are pretty easy to operate. So now, if we multiply 0.002 times, oh, we're still operating at a loss. So let's do, instead of 2, let's go down to 1. Oh, being kicked off. Here's what we'll do. Always allow. Ready? Okay, so let's revise this example, and we'll keep the 5 cents per cup. The lemonade mix has got to be cheaper, so it's going to be something that is 1/100th of a cent. So it's going to be 0.005. We still get a, so we're going to just keep going with this. I apologize. So 0.0005 times, and then our 500 units that we're selling, right? That 500 is going to turn into 250,000. There we go. Oh, wait, hold on. 500 times 500, Gregory. Yeah, 250,000. All right, we're going to do this all out here.
Should be 100.
100, yeah. Okay, thank you. So we put this 500 in here. We get 500 squared there. 500 squared is 250,000. So then when we take 0.0005 times 250,000, it gives us what I wanted, $125. So we have $125 that's coming from squeezing the lemons and all of the sugar. We have $25 that's coming from the cups. When we add up all of our costs, we're going to have $150 total. And so then when we calculate our profit, which is equal to that revenue minus the costs, quite simply, it's going to be 250 minus this 150, which gives us a profit of $100. So a fair bit of work in terms of just kind of understanding what's going on, right? But this is all just algebra, right? Muddle through it as I did. This is all just algebra. So I just wanted to make sure that we all are understanding kind of what these different functions mean in terms of, some of them are going to be increasing just in the units that we sell, right? 0.05 to the x. And some of them are going to be increasing at an increasing rate, right? When we have this square term there, that's telling me that the more widgets they produce, the more cups of lemonade they produce, the higher costs or the greater errors they're going to have, which is going to influence the cost function. It's going to make the cost higher than if it was just purely linear. So what if we wanted to solve for something like this using calculus, right? So let's do a new example this time. And this time we're going to talk about economists' favorite things, widgets. And so we have this widget factory, and we're told that the revenue function, the R of x, is equal to 50x minus 0.1 x squared. And we're told that the cost function is going to be, again, linear in x with no fixed costs, and it's going to have some costs that are increasing as x increases. Increasing at an increasing rate as x increases. And so this is the one where, the more that they produce, the higher chances that the widgets disappear or are broken, whatever the case may be. And so there's two ways that we can use calculus in order to figure out profit maximization. So we can write profit out, and we can use these functions. And then we can subtract, and we have to use parentheses for the cost because that negative sign from the subtraction gets distributed, right? So this negative sign is going to apply not just to the 30, but also to the 0.2 x squared. So we can write out our whole profit function, right? And our whole profit function is going to look something like, and I'm not going to pause the class so that I can give us the exact map of it, but these profit functions start out small and they peak at a certain area and they come back down. And this is units of widgets. So what we're trying to find, right, we're trying to find the place where the maximum is, right? The local maximum. And when we have a quadratic term and we're trying to find the local maximum, what are we going to do? We're going to set the derivative. We're going to take the derivative of it, and we're going to set it equal to 0. But why are we going to do that? So let's look at that graphically real quick. So this is something in economics we do all the time. We're constantly taking derivatives of things and setting them equal to 0 and solving for them. And so the reason why, and so this is going to be our rate of profit. And again, the units of widgets. And so we can take a look at the slope of this profit curve, right? And we see that the slope of the profit curve is positive, but the slope is declining as we're increasing, right? So there's some sort of limit to our profit. There's some sort of limit to how many widgets we can produce. We can't just produce widgets at a profit forever. We only have so much space. We only have so many people. We only have so many machines. We only have so much time, right? Maybe we do have unlimited machines and people and land and stuff like that. We literally only have 24 hours a day, 7 days a week, right? So there's some sort of constraint. And so we're trying to find where that constraint kicks in. And the way we do that is by looking at these rates of change. And so we're trying to find that point where the slope goes from positive to negative. So now on this side, we've got negative slopes, right? And so the corresponding first derivative of this would be right here. The slope is pretty high, right? The slope is, I think that's at a rate of 3, a rise of 3 for a run of 1. Whereas over here, it's maybe more like 2. And then here it's maybe more like 1. And right here is where we see that switch, right? And then over here, we start to see a slightly negative slope. And then here we get a more negative slope. And here we get an even more negative slope. And so when we put together the line connecting these three, we're going to have it crossing, hopefully, right at the, I think I did it right, right at the topmost point of that profit curve. So we're taking the derivative and we're setting it equal to 0 because essentially it's a shortcut for us to figure out that local maximum. Instead of, having a chart where we say, okay, well, if we do 1, how much is profit? If we do 2, how much is profit? If we do 3, right? We could do that in Excel, but that would take a lot of time. So this is our shortcut. And so there's 2 real ways that we can do this shortcut. The first of which is we can just take this full equation. We can combine some of the parts to it, right? So for instance, if we combined like parts here, right, 50 minus 30 is 20x. And again, if we combine like parts, 0.2 minus 0.1 is plus 0.1 x squared. And so what we do here now is this is our profit function. We want to get the rate of profit, right? So we want to get the, so if this is our P, well, actually P is not great. What do you guys use for profit? I mean, we use pi.
I normally use P, but P bold.
No, we can use P. P's great. P usually is for price, right? You know what I mean? But when we have like P of X, then we know it's profit, right? So we've got P of X, and so now let's do P prime of X, right? First derivative just with respect to X. So again, on your own, just do that simple chain rule derivative. So we end up with 20 plus 0.2 x to the first power. And so now what we do with this, and I do apologize because this example is going to come out with a negative number, which is not going to make a ton of sense, but the calculus is the same.
Something's gone wrong. That profit shouldn't have a positive slope.
Right. Something has indeed gone wrong.
Negative 0.1x squared minus 0.2x squared is minus 0.3x squared.
Thank you. I made the classic mistake I told everybody not to make. That was a learning moment. I did that on purpose. That was so Dr. Moses could help us out. Thank you, Dr. Moses, with the tag team hit. I usually teach my classes at 2, not 9, so I'm going to use that as my excuse today.
So the derivative is 0.6.
Thank you. Okay. So this negative gets applied here. We don't forget. So it's 0.3, which then, when we take that 2 and we multiply it by the 0.3, we get minus 0.6 x to the 1. And so now what we do is we now set p prime of x equal to 0 and then solve for x. And so if we set this equal to 0, that just means we replace this right-hand side with 0, right? So then this becomes 20 minus 0.6 x to the 1, you don't need to say to the 1, equal to 0. We're going to move 0.6x to each side. We're going to end up getting 20 equals 0.6x. We're going to divide both sides by 0.6, and we're going to end up with the nice round number of 12. So 12 is going to be the amount that gives us, yes?
20 divided by 0.6 must be bigger than 20 divided.
33.333. Thank you. I did calculator without looking, and it ruined me. Yeah, that's a good gut check, right? Whenever you're dividing any kind of whole number by a fraction, that's going to be greater than that same whole number. Just a good general rule to gut check yourself with whenever you're doing that. So this will not be 12. This will be 33.3. So this is one way for us to do it. And to be frank, you know, I wouldn't recommend this way. This way seems like it has more steps. If this way makes sense to you, then that's great. But we do have a nice shortcut that we're going to learn about in the next part. So let's go ahead and see if I can kind of, nope. Let's see, can I lasso these kind of things together? Never mind. All right, so we're just going to recopy them. Oh, actually, we can just erase this stuff. We've got it in our notes. Let's leave the graph because the notion is the same with the graph. Let's get rid of all the other distracting stuff. Okay. So the other way that we can do this, right, we can take our profit function where this is our revenue function, this is our cost function, right? And we can do this maximization ahead of time, right? So instead of writing the equation out, we can say, well, we already know we're going to take the first derivative of profit. And because of my derivative rules, since these things are only terms being added or subtracted, right? They're not being multiplied together. So I can just kind of pass that derivative through onto both of them, right? So essentially there's a middle step here where you're taking the derivative of Rx minus C of x with respect to x. And then you can, correct me if I'm wrong, Dr. Moses, but you can then kind of, same way you do this with stuff, you can circle this around for each one of these and split it up like that. So it's the same way. So this, it looks more complicated, but it's the same situation when you have something that's like, I'm trying to think, 3 times 1/3 plus 2/3, right? And then you could say that's just 3 times 1/3 plus 3 times 2/3. So you can take that part and then you can take that part. So we're just doing that same thing, but we're doing it with more generic equations. And then again, we know what's the whole point of this. The point of this is not necessarily to have a nice profit function so that I can put it in Excel and look at what the profit is at each one. No, I want to know what's maximizing the profit, right? So I'm going to already be setting P prime of x equal to 0. I know that that's my process in my profit maximization. So I can just do that before I even put in any specific equations that we have here. And so replacing P prime with 0, we get 0 equals R prime of x minus C prime of x. And I've been holding out on you, some of you from my econ classes or have taken econ classes either before or in high school, you might be saying, oh, these R primes and these C primes, they have names, right? And R prime is also known in economics as our marginal revenue. And quite simply, it's just the additional or the incremental revenue that you get after you sell an additional unit. Our C prime, the rate at which our costs change, well, this thing is nothing more than our marginal cost. And so when we solve for either one of these, right, when we get rid of the 0 on the other side of the equal sign, and when we replace these terms for their economic values, we end up getting the golden rule in economics, which is that your profit maximization output is always where your marginal revenue is equal to your marginal cost. And to be fair, this equal to must be a greater than or equal to, right? Because sometimes we're going to be talking about things like automobiles. And when we have cost functions and revenue functions that are this specific, we may come up with an answer that says 12.2 automobiles, right? How do you produce 0.2 automobiles? You can't, right? So that's why it's the last whole value where the marginal revenue is greater than the marginal cost. But again, we don't need to necessarily focus on the greater than right now because I want to tie this all back to the R prime and the C prime, right? So this marginal revenue equals marginal cost is the same as if we just added C prime to this side. These annihilate each other. And then we end up with C prime of X on the Y side and R prime of X on the X side. And as we know, because of the law of reflexivity, this also means R prime of X is equal to C prime of X, which is just that marginal revenue equals marginal cost. So this is just another way to do effectively that same process, but it usually goes a lot quicker. So we're going to do it as well, and we're going to come out with the same 33.3 number. So the way that we start this one is we just kind of start with asking ourselves, what is our marginal revenue? Our marginal revenue is going to be that first derivative of R with respect to X. And so it's going to be 50 minus 0.1 times 2, 0.2 X, just to the 1 power. And then we ask ourselves, okay, what is our marginal cost? Our marginal cost is going to be our C prime of X. So this is going to be 30 plus 0.4 X. Because we have this 0.2 that's multiplied by this 0.02 over here. Sorry, I know the glare is kind of not great. I would love to just be able to copy these over, but that's not in the cards. So 50 minus 0.1 x squared, 30x plus 0.2 x squared. We take the derivative, it's 50 minus 0.2 x and 30 plus 0.4 x. And now that we have these, well, now we know that we can set them equal to 0 in order to find our x star, our profit maximizing. Or sorry, not set them equal to 0, we set them equal to each other. Apologies. And so we're going to end up with 50 minus 0.2x is equal to 30 plus 0.4x. We're going to group like terms. Well, actually, that's more confusing than anything. We're going to subtract 30 from this side. This 30 annihilates. This becomes 20. We're going to then subtract 0.2x from each side.
Teacher.
Yes.
To undo subtraction, you use addition.
Thank you. I really want to just get that amount wrong, don't I? So we've got 20 minus 0.2x. To undo subtraction, we use addition to annihilate it. And then add that to both sides. 0.4 plus 0.6, 0.4 plus 0.2, slow down, is equal to 0.6. And we have just 20 left over here. So then when we divide 20 by a number less than 20, we end up with a number less than 1, we end up with a number greater than 20. 20 divided by 0.6 is equal to 33.3. Repeating, this is the amount of widgets that maximize profit. And so again, we cannot create a third of a widget. Nobody wants to buy a third of a toaster, right? So the answer, you know, if it was a multiple choice test, or I mean, even if it was a short answer test, the answer would not be 33.3 widgets, right? You'd only use decimals if we're talking about like pounds of wheat or corn or something like that, right? Things that are actually divisible. So you would just say, well, it's the 33rd widget. So we're going to do 33 widgets because that's the one that is the last one with a marginal revenue greater than the marginal cost. And if we don't believe this, right, we can always, create our profit function again, and we can plug in 33 and we can plug in 34, right? As just a way for us to double check ourselves. So again, our profit function, P of x, is equal to 50x minus 0.1x squared minus 30x plus 0.2x squared. And so this is going to be 50x minus 30x minus 0.1x squared minus 0.2x squared. So this whole thing is going to be 80x minus 0.3x squared. And so now we're going to evaluate, yep. Yeah, thank you, 20x. And so now we're going to evaluate this profit function at 32. We'll evaluate it at 33, and then we'll evaluate it at 34, just to make sure that it is indeed the amount that's giving us the highest profits, right? Wait. So what we find is that indeed, at 33, we end up with a profit of $333.33. So that is profit maximization using economics. Thank you all for your patience as we stumbled through some of those algebraic mistakes together and some of the numbers. Thank you, Dr. Moses, for your help. But if you guys ever have any questions on this, I have lots more resources, lots of great places to direct you to. It's really just, there's two ways to do it. They both should come to the same answer, and you should be able to check the answer and make sure that that is actually the maximum around those points. Any questions? All right, cool. Anything else for him?
No,
nope.
Thank you very much
all right.
for your time.
You're so welcome. My pleasure. Thank you all. And then this will be recorded on the YouTube channel for you to watch later as well.